Hi everyone, this is Professor Sebastian back with our Calculus 3 class notes. We are moving into section 13.2. We are on page 29 of our class notes. Okay, this is where we're going to talk about integrals of vector functions, and then we're also going to bring up a specific example, projectile motion, which is actually covered in Calc 1, but now we can talk about it more in at least a two-dimensional sense, not just a one-dimensional sense. Okay, so definition. The indefinite integral of r, where r is a vector valued function with respect to t, is the set of all antiderivatives of that vector valued function r. So if capital R is any antiderivative of little r, our vector valued function that we want the indefinite integral of, then the indefinite integral of r of t dt is capital R of t plus a constant, but now that constant is a vector itself. So that looks familiar to what we saw with the fundamental theorem of calculus. The usual arithmetic rules for indefinite integrals apply. Now, just like we could differentiate each piece of the vector valued function r of t, we can integrate each piece separately as well. So if I want the integral, that should be a bold r of t, I apologize. That should be a bold, and also notice I misnumbered the examples, so this really should be example 27, but I'll just keep it, since I've already finished these notes, and hand them to you, example 26. Just know that we're in section 13.2 and I misnumbered them. We already had example 26. So this is a second example 26. The indefinite integral of r of t, that should be bold, right? Because it's a vector value function. Anyways, you can see that here. It's cosine of t in the I direction plus j in the plus 1 in the j direction minus 2t in the k direction, dt. So you just integrate each piece separately. So we integrate cosine of d dt, and that will be in the I direction. So that's sine of t plus some arbitrary constant, right? Remember that from doing indefinite integrals. And then the integral of 1 dt is t plus another arbitrary constant. We can't label it the same because it could be a different constant. And then that's in the j direction minus the integral of 2t, which is t squared, plus another arbitrary constant, c3, in the k direction. So that gives us sine of t in the I direction plus t in the j direction minus t squared in the k direction plus a constant vector, where that constant vector, the way I wrote things, is c1i plus c2j minus c3. Since I'm distributing the minus here, k. It doesn't really matter if I called that plus c3 because it's an arbitrary unknown constant. So definition, the fundamental theorem of calculus for continuous vector functions says then that if I want to integrate from a to b, instead of having an indefinite integral, now I have a definite integral. I just plug in b, find my antiderivative, plug in b, and then subtract plugging in a, just like we did with regular functions instead of vector value functions. So that means you integrate each piece separately and apply the fundamental theorem of calculus. So in example 27, let's evaluate the definite integral of r of t equals cosine of ti plus j minus 2tk. So same vector value function from example 26 above, but this time from t equals 0 to t equals pi. So we write it like this. Integrate each piece from 0 to pi. Apply the fundamental theorem. So that's sine of pi minus sine of 0, which is 0 minus 0. So it's just 0i. Then it's t evaluated from 0 to pi. So it's pi minus 0, which is just pi. So that's pi in the j direction. And then its integral of 2t is t squared. So it's t squared from 0 to pi minus sign in front of it. That's pi squared minus 0. So it's minus pi squared in the k direction. Notice we did not work with our constant function because it would go away with each piece. So we don't need to have that, of course.